Hi everyone, how are you?
Good.
Good to hear. Okay, guys. Okay, guys. I checked out the results of the quiz, and one of you solved all the questions without any error. Congratulations. Who was that?
It was me.
Islam. Yeah, I suspected that. I will tell you some background information soon. Okay, and two further students made only one error. So basically, three out of six guys uh, reached the minimum 75% today. That's not bad, but you can do even better, I guess. I'm telling this because I checked out the activity in the e-learning site. You know, in the e-learning site, I'm sharing closing tests with you every week. And in this system, in this Moodle system, I can check out the activity and the results of results by you. And actually, as far as I can see, probably only Islam solved the very last test. So you could and you should practice more in general. Please do, and then you can collect more points. This is my suggestion. Okay.
Okay, thanks.
Okay. And by the way, do you have any question regarding the test? Uh,
When is the test?
I mean the quiz. The quiz. Do you have any question regarding the quiz?
I think it's all like you have to memorize the laws.
Mm-hmm. Yeah, you can memorize the laws. Of course, those laws are logical, so you can also figure it out how they work. Of course, you should read them first and apply them in certain exercises first. Okay, in the quiz there were two more difficult questions, I think. One with distributivity and another one with absorption, I think. And yeah, those were more difficult compared to the other questions, but quite essential. I mean, distributivity, the law of distributivity is really, really essential. We already experienced it in the previous week, and we will use the law of distributivity in the long run. So, for example, today we are going to learn about normal forms, and also when we want to translate a formula to a certain normal form, we have to apply, for example, the law of distributivity here. So you should remember at least how this law works. And about the law of absorption, yeah, this law is really handy because you can make simplifications in your exercises, so you can make your situation easier if you can simplify parts of the formula out. And the law of absorption is really cool because of that. It can simplify out the longer part of the formula immediately. Okay, so there are no questions regarding the quiz. Nope. Okay then. So let me start with the new topic. Let me ask you if we already learned about those normal forms in the exercise class last week, or we didn't.
Yeah, we learned, I think, in the last week.
Last week we did learn about CNF or DNF.
Yeah,
Yeah,
just the beginner, just not the general definition.
I see. Okay, fine. Thank you. Okay, so this is the new topic for this lecture. Actually, soon, I mean, today or tomorrow, I will upload the new module about this topic and also closing test. So please again read the module and solve the exercises there and stuff. And also in the practice class, when is it? It's tomorrow. We will solve exercises regarding those normal forms. So I'm not going to talk about everything here, but I'm going to talk about the theory behind, as you just suggested. So we are going to talk about those definitions and also a cool algorithm which is called the Zetin transformation, which is not part of the exercise class. So this is only for the lecture. So this is the plan for today, to talk about Zetin transformation. I will show you now also an example, an exercise, and furthermore to talk about those definitions because they are not part of the exercise class either. Okay, about normal forms. So there are so many normal forms in logic. I give an introduction in the module I'm going to publish soon, so you will be able to read it. In this subject, we only learn about two normal forms, CNF and DNF. Both have the same goals. So basically, we want to make our formulas easier to evaluate, easier to see what's in the formula. And also, if you check out the last item here, those normal forms work as standard input formats for softwares which are able to solve logic statements. Later, in 2 weeks, I think, I will show you such softwares, and we are going to use them for solving statements. And they all use actually CNF as an input format. This is why we are learning about at least CNF. Actually, the main focus is on CNF. Okay, but what are those? So both CNF and DNF are so-called normal forms. And I think this is something I already talked about, why we call them conjunctive and disjunctive normal form. Have I already talked about it before?
Yes, you do.
Okay, thank you. So I'm not going to repeat myself. In the exercise class, you will learn about an algorithm which is able to transform any formula either to CNF or DNF. And actually, we already did, as far as I can remember. But there are three algorithms which we learn about here in the lecture. So here is one which is based on truth tables. You know what truth tables are. So just imagine that I give you a formula, very ugly and very long one. First, you have to construct a truth table for that formula, and after that, from the truth table, you can generate either a DNF or a CNF. If you do the transformation in this way, you get a so-called full DNF or full CNF. I'm not explaining now why we call them full. This is part of the module in the lecture notes I'm going to publish soon. There you will find examples, exercises, everything. So this is not a difficult algorithm, but it has a very major drawback. Just think of a truth table. So truth tables are typically huge. If you have plenty of variables in your formulas, the truth table immediately just blows up. It's really huge. Therefore, we immediately learn about the other algorithm in the exercise class, which is much more optimized. And well, if you look at it, it really looks like an algorithm. It consists of a series of steps, you see. And if you check out those steps, basically each of them applies a certain law you already know. For example, how can we eliminate XORs, equivalencies, implications? This is really important. By the way, you have to eliminate all the three of those operators from your formula, because in the CNF and DNF you can only use conjunctions, disjunctions, and negations, nothing else.
Professor?
Yeah?
The first thing is that you are not sharing your screen.
Oh, geez, thanks. Oh.
And the second one is that can I share mine because I have a question in the module?
Yeah, okay. Then please share your screen first. Okay, it took some time.
Yeah. Is it working now?
Yeah, let me see. So it took some time. You warned me. I don't share my screen anyway. Thank you. Okay, I can see your screen.
So like which interpretation did we do for the B and negation B and the Q? Like I can see that there is only I have to use 0 or 1. So how did this answer came out?
From 30.
So basically the question ask when this formula is true. Oh, no. So no. These are the So in each interpretation, what is the value of this formula? And I guess the first row is about when P and Q are both false, 0, 0. The next interpretation is when P is 0, Q is true. Anyway, so the last option is supposed to be the correct option. Why? Yeah, this is true because this formula is always true. Do you understand why?
But my question is that like I made a truth table for this, and this is the answer of it?
Yes.
So it doesn't matter if I started with 0, 0 or 0, 1. Either way, it's going to be all 1.
Yes.
But I mean, like for example, if the answer is this, how do I know that I will get 1, 1 in the first row, not the second one?
No.
But
in that case, you cannot know.
So if I like, for example, get a question like that, the hint for me is that to choose all 1 or 0.
Yeah. Yeah,
Okay.
you hacked our system. Congratulations. Yes.
Yeah, because like the first question is logic. Okay, that's an equation. But when I came to this, I didn't know like if I made a truth table, would this be or this or this?
Yeah.
Yeah, so this explains it.
Yeah.
Okay,
Okay.
thanks.
Thank you. Okay, let me share my screen then. Okay, can you see me now?
Yes.
Yes.
Okay, so next time, please warn me if I'm not sharing my screen. I mean, sooner, please. Okay, back to the slides. So where were I? Yeah, here. So I was talking about this first algorithm, which is based on truth tables, and this is also explained in the module I'm going to share with you. Then I was talking about this algorithm. This is what you learn about in the practice class, exercise class. And yeah, the first three steps are about eliminating operators which are prohibited in a CNF or a DNF, because in a CNF and a DNF only conjunctions, disjunctions, and negations are allowed. So therefore, first we have to eliminate the remaining operators. And furthermore, in step 4, you have to move the negations inward. I mean, if you check out a CNF and a DNF, negations, it's written here. So negations are allowed to use only in front of variables, nowhere else, only in front of variables. So this means if you have a negation,
We have to apply it.
yeah, you have to apply the De Morgan laws to move them inward towards of your variables. Okay, but this is algorithm we are going to practice in the exercise class. So, and there is an extra step which you might or might not need. It depends on the situation, and this is based on distributivity. Furthermore, meanwhile, I mean, whichever step you apply, you always have to notice if some simplification can be done, because if you can simplify anything out, this pays off immediately. It makes your situation easier. So try to shrink your formulas whenever you can, and then this very last step, the application of distributivity, will be a little bit easier. It's the bad. This is the bad guy actually. This last step, because it increases the formula size. Therefore, again, it pays off if you can simplify something before that. Okay, so this is the second algorithm we learn about, also in the lecture notes and also in the exercise class. And there is a third one. I already mentioned this in the beginning of our lecture, which is called the Zetin transformation. So this is the one I'm going to talk about today in details. But first, back to those slides, this and that. So first, let's talk about the definitions. Actually, we were talking about CNF and DNF, but we have not defined yet what they are exactly. And this is something we need on the lecture. So here we talk about the theoretical part as well. So when you come to me to take the exam, you will also have to talk about the definitions. Okay. So let's talk about the definitions. They are not that difficult. However, you must understand them. Okay, let's first check out the definition of a DNF. You know, DNF means a disjunctive normal form. So if you check out this DNF here, let me just make the red stuff disappear. You will see that it's basically starts with variables here and there and there. So the variables are on the lowest level, non-negated or negated form, in a non-negated or a negated form. So these negated and non-negated variables are on the lowest level. So we call them literals. So we call all of them literals. A literal is either a Boolean variable or a negation of a Boolean variable. This is the definition. I mean, this is such an easy definition. You must remember that. Okay, so these are the literals here. Then the next layer of the formula is this one. So we basically connect our literals with these, with conjunctions here or there, for example. So these are what we call conjunction of literals, basically. They look like that. You just connect all your literals with with conjunction. Here, it is important to specify that each li is a literal, and that's it. So this defines the stuff between parentheses in the DNF, conjunction of literals. Actually, it has an alternative name. Let me introduce it here. So in computer science, the conjunction of literals is also called as a cube. I don't know why. This is an alternative name. Okay. So back to this example, we have 3 cubes here. This one consisting of 2 literals, this one consisting of 3 literals, and there is a third one consisting of only 1 literal. This is also allowed. This is also allowed because here we use k as the notation for the number of literals inside the cube, and yeah, this is the constraint for k. K must be at least 0. So 3 is okay, 2 is okay, 1 is okay, 168 is okay, and also 0 is okay as well. In the lecture notes, I will write about how to interpret a cube with 0 literals. I'm not going to talk about this now. It's not that important. You will read the corresponding content in the lecture notes in the new module. Okay, so far, don't you have any question?
So can you repeat what you said about k, mean of k?
What is the meaning of k?
Yeah, I didn't get what you said.
So k is the number of literals inside the cube. So for example here, for this cube, for the first cube, k equals to 2, right? K equals to 2. This is the number of literals in this cube. So let's check out the second cube.
3.
Yeah, k equals to 3.
Okay.
And similarly, for the last cube, k equals to 1. This is 1, sorry.
Okay.
Okay. Okay, so we already defined the cubes. Now let's do the final touch here. So I have 3 cubes here. Let's connect them with this junction. This make this normal form disjunctive. So let's define what the disjunctive normal form DNF is. We just simply connect cubes actually with this junction. Each E is a cube or conjunction of literals, and here N denotes the number of cubes, which is again at least 0. So for example here, how many cubes do we have?
3.
3, yeah. N equals to 3 in this case. Yeah, but N can be 4 or 5 or 1000 or only 1 or even 0. So it's also allowed to have an empty DNF. I will also tell you in the new module what does it mean actually. It's not that important now. Okay. So this is the definition of DNF. Do you understand that?
Yes.
Or you don't understand anything?
We understand.
The definition is clear.
Okay, so what's not clear?
Not clear is how to
Correct.
change from DNF to CNF.
I see. Okay, in a minute I'm going to show this to you, okay? Before that, let's talk about CNF, the definition of CNF. Rashid, do you want to ask something?
No.
Okay. Okay, so let's check out the definition of CNF first. Now I'm switching between those two slides. So this is the definition of DNF. This is the definition of CNF. So as you can see, they are quite alike. Actually, the definition of literal does not change. Sorry. What changes? Well, first of all, inside the parentheses, now we have disjunction and not conjunctions. So in a DNF, we have conjunctions between our literals. In a CNF, we have disjunctions. But everything is the same. Here, let me draw your attention to this very important term, close. So I'm going to use this term a lot because, as I already told you, CNF is the more important normal form. DNF is not that important. CNF is the important one. And a CNF consists of clauses, lots of clauses. So for example, here in this example, we have one clause, another clause, and the third clause. So we have 3 clauses. They look like those. Actually, CNF is also called clause. Oh, this is really difficult to write like that. A closed normal form. This is also the abbreviation of a conjunctive normal form and also a closed normal form. Anyway, so now we have clauses, and those clauses are connected with conjunctions. So we use disjunctions and conjunctions in the other way around compared to DNF, and that's the only difference between those two normal forms. Okay, so back to Oleg's question. So what if what if I'm telling you to translate a formula to CNF, and unfortunately after you apply all those 4 steps you get a DNF. Then you have to translate your DNF to CNF. This is what you want to know how to do, right, Oleg?
Yeah.
Okay. So again, you can do this by applying the law of distributivity. Because if you check out, so for example, this looks like a DNF here. And if you want to translate it to a CNF, you basically have to swap, it's written there, swap conjunctions with disjunctions. So inside the parentheses, you must have disjunctions and conjunctions between those 2 clauses actually. Okay, let's see an example here. Okay, let me give you an example. So for example, if I have a disjunction like, I don't know, X. So if I have a DNF, then inside the parentheses, what kind of operators I have to use inside the parentheses for a DNF?
Conjunction.
No,
Or
no, and. Inside the parentheses, I have to use,
Conjunction.
yes, conjunction. And outside of the parentheses, I have to use,
Disjunction.
yes, disjunction, yeah. So let's suppose we have this kind of DNF like, I don't know, X, and let's make it more difficult, Y, okay. And you want to translate it to a CNF. How to do that? This is the question. So the easiest way is to
apply De Morgan.
No, not De Morgan. Distributivity.
Distributivity.
You have to apply distributivity, which basically construct pairs of those literals. So basically you have to pair each of those 2 literals with each of those 3
True.
literals, right? So for example, you pair X with Z. X with Z. And can you tell me what operator to put in, between?
Or.
Exactly.
Or.
Yeah, exactly. So I connect X, literal from the first cube, with Z, literal from the second cube, and I make pairs of them by applying this operator between. Okay, how to continue?
And.
Exactly. And now let's switch to the second clause. For example,
Or negation.
X
or
or
X.
not X.
Okay.
X or X should be, I think.
X
X.
or negation
What?
X. This is also one of the pairs, right? One of the clauses, because we take one
Yeah.
literal from this cube and another literal from this cube, and we connect them with this junction. And basically this is how you continue. You just take all the pairs. How many clauses we get at the end in this case?
6.
6. Actually this is 3, and we get 3 more literals. Let me use copy and paste. So the same clauses, but with negation y,
Y.
yes, as the first literal here. So this is it. Now you have a you have a CNF.
All right. Thanks.
Okay, of course, you could simplify this formula further. For example, if you
One
excuse me?
is equal 1. X or
Yes.
negation 1.
Yes, this equals to 1, exactly. And then you can simplify this out. And similarly, you can simplify this last close out. So I think this will be the simplest CNF at the end. Okay. Is there any other question regarding this step? I mean the 5th step here.
What if we have like 4 clauses? Because in the homework we have 4 clauses to convert to CNF.
You mean here you have not only 2 but 4?
Yes.
Cubes. Okay.
Cubes. Okay.
Well, okay, let's see an example. Well, first of all, if you can simplify, please do. Maybe if you simplify, you can reduce the number of your cubes. But if you cannot, and you have not 2 but 3 or 4 cubes or more, like, I don't know, not z and x, then, well, it's easy. So first of all, I translated the first 2 to a CNF. So this is what I got. And this is now connected with the rest of the formula. So we are not ready yet. So far, I just translated the first 2 cubes into CNF. Okay, so what to do now? Well, again, you have to pair the, how to say, pair the elements of this conjunction with all the elements of this conjunction. So it looks funnier. This conjunction have such elements, x or z, x or y. And those must be paired with those 2 literals. So let me show you. This is a very ugly step. I mean, this 5th step. This can make the formula really ugly and very long. But anyway, sometimes we must use them. So x or z must be paired with not z, and actually all of those clauses. So this clause should be paired with this literal. This clause must be paired with the same literal. So basically, this is what you get here. Okay, so far, do you understand that?
Yes.
Okay,
Thank
and
you.
how to continue this, because we are not ready yet?
Doing
We
the same
have
with
to pair
X.
X.
Yes, you have to do the same with x. So we have pair those 4 clauses with x as well. Exactly, so this makes the formula so huge. But hopefully we can simplify something out. So, oh geez, I cannot fit on the screen. So, okay, so here we have x, and x.
think you can zoom out.
Yeah, I have no other option. No, I cannot. Okay, then just try to. Oh, come on! I cannot break a line. Okay, so you can imagine that, right?
Yes, thank you very much.
Okay. Of course, now probably you can simplify again. So, for example, this part of the formula can be simplified, and there are plenty of more which can be simplified. For example, this one, we have a double x. So, for example, here I can erase one of them. Anyway, the result is still ugly, but it's in CNF. That's the point. Okay, any other question? Okay then, as I already told you, in the exercise class, we will use the same algorithm plenty of times, so we will practice more. Let me now switch to the third algorithm, which, as I already mentioned, won't be part of the exercise class. So we just learn about the Zetin transformation here and now. So why do we learn about the third type of transformation? Because the algorithm, the previous algorithm, this one, is exponential. It means that you know what exponential means. For example, the spread of coronavirus is exponential. It means that the number of infections increases in a very drastic way, like that. Or also, you know, there are other exponential phenomena. For example, the mating of rats is also an exponential phenomenon, or how the fetus inside a woman's belly grows. It's an exponential kind of phenomenon. Okay, anyway, unfortunately, this algorithm is also exponential, which results in very huge CNFs and DNFs at the end. It might result in very huge, exponentially large CNFs and DNFs. And this is due to laws like distributivity and also the law of the rule for equivalence. Here, if you look at those rules, you might notice that basically they duplicate certain parts of the formula. For example, P equivalent with Q duplicates both P and Q, right? So you have to write them twice. Speaking of distributivity, it duplicates P. So this makes really ugly the algorithm. This makes the previous algorithm really ugly and exponential. And in practice, in industry, you have huge formulas. And there, actually, the previous algorithm typically generates a huge number, an intractable number of clauses and cubes. Actually, in the real life in industry, the third type of algorithm is used because it's not exponential, it's linear. You know, the linear function is like that. It's like a line. It's not that steep than the exponential function. It's much more moderate. Okay, so let me talk about this transformation. This guy, Zetin, introduced this algorithm as a kind of simplification for logic circuits. You already learned that logic formulas can be visualized as logic circuits, and it's easier for me and for Zitin to explain this algorithm if we visualize our formula as a logic circuit. Okay, so the idea is the following. In your circuit, there are logic gates like this one here. By the way, does any of you know what logic gate this is?
OR gate.
This is OR gate, are you sure? Yes, it is. Here it is.
Yes.
This is the OR gate, exactly. And how about this one? This is the AND gate.
gate.
Exactly, AND gate. So you already know the notation of those gates, but here you can find on this slide all of them. For example, it's easy to remember if you have a nipple in front of the gate, it's negated, like NAND or NOR or NXOR. Actually, NXOR is really important because it represents equivalence. You know, equivalence is the same as a negated XOR. Anyway, so you take all your gates and introduce brand new variables that represent the outputs of those gates. So for example, I introduce x1 to represent the output of this OR gate. And this is what I do. I give a definition of x1. x1 is defined as P or Q, right? P or Q. Or x2 is defined as the end connection of what? Of x1 and R. x2 is defined, is equivalent with x1 and R. And this is how you keep going. You just keep introducing your variables and define them as equivalences, basically. So for example, here, can you tell me how to define x5? x5, how to define it?
It's x3 or x4.
That's it.
Not X. Yes.
This is also good, actually. I think I have an idea what you meant, but yeah, let me just write the first of your solutions. So x5 is equivalent with x3 or x3 or x4, exactly. I don't really like the this formula editor of PowerPoint. Yeah, so this is it. Or we could also how to say, plug in the definition of x3, which is basically negation. How to write negation here? Negation x2. Yeah, no, this is, where is it? Okay, maybe here. Okay, this is also a good solution here. Okay, so you get it, don't you? Okay, then let's continue. So basically, the main idea of the Zitin transformation is to substitute subformulas inside your huge formula. So this is your original, probably huge formula with some subformula inside. This subformula must be a non-literal subformula. So a compound subformula, for example, implication or a conjunction or a exclusive or. And basically you take out this subformula and substitute it with a brand new variable which you exchange, which you, how to say, so basically you exchange A with X inside your original formula. Okay, I hope you more or less understand that. I will show you an example very soon. So basically the resulting formula will look like this. You take your entire formula A, you substitute it with x1, therefore in front I'm going to conjunct x1 to those equivalences, and well, the rest of the formula consists of a huge number of equivalences. I would like to draw your attention that this formula looks quite nice already, because we have only conjunctions here. Conjunction, conjunction, conjunction. The outermost operators are all conjunctions, so it's almost a CNF. Almost a CNF. We only need to translate the equivalences to CNFs. So this we are going to convert to a CNF. Then you plug this CNF in, and that's it. After that, you convert this part to CNF. So basically, you can translate, as I'm writing at the bottom, you can translate each of the equivalences to CNF separately, and then plug them in the formula. And at the end, you get a full you get a CNF for your entire formula. So this is very nice that you can translate the formulas inside the parentheses separately. Okay, something else here. You don't really have to think much about how to translate those equivalences to CNFs, because they look quite alike. Actually, on the left hand side, inside such an equivalence, so again, on the left hand side, in each of the equivalences, you have one single variable. x1, x2, and x3 are only variables. On the right hand side, you have either a conjunction with two operands, or a disjunction with two operands, or an equivalence with two operands. So they also look quite alike. Therefore, if you don't want to think too much, you can just use tables you can find in the internet which can help you. So here I linked such a table from Wikipedia. Here it is, which tells you, without thinking too much, how to translate, for example, an AND connection to CNF. Just look at the first one. So here the table uses different notations. It says if you have a variable C, which is equivalent or equal to A multiplied by B, actually multiplication denotes conjunction and logical and. This is also another notation for conjunction, multiplication. Similarly, addition is another notation for disjunction, and so on. So anyway, here you have a variable C, which is equivalent with A and B. Then this is the CNF you can immediately generate. It consists of three clauses, and that's it. And the same is given for disjunction or XOR or equivalence in the very last row. You see? Okay, so let me show you an example, if you don't have any question at this point. Nope. Okay, so now I'm going to show you the Zitin transformation, how to use it. So here I already prepared a very nice formula here. So this is what we are going to translate to, to CNF. Sitting transformation is only about translating something to CNF. How to do this? Well, if you remember, we are going to introduce brand new variables like that. So I would like to emphasize this part of the slide here. So we are going to move from outside to inside. So we've introduced first variable for the outermost operator, this implication. So this x1 is going to represent the output of this implication. Then we are going to go deeper. So let me introduce the second variable for this XOR. XOR, and similarly, you know what? Let me just use parentheses here.
Your screen froze.
It's frozen?
Yeah, it's frozen.
Okay.
Everything.
It's working now.
It's working.
Okay. Let me share it again. Is it working?
Yes.
Okay. So I introduced the first variable x1 for implication, x2 to the left-hand side of the implication, so basically for representing this XOR, and I also introduced x3 for representing this conjunction. And okay, and let's see how we proceed. So first, let's start with x1 and conjunct it with the definition of x1. So basically, x1 represents the entire formula. Actually, it is conjuncted with the definition of this variable, which is what? Well, it's an implication. X1 is an implication of what? X2 implies x3. Okay. Do you understand that? Okay, so
How did we switch it from B Zor negation Q to x1 and x1 equivalence? Like, where did the symbol came from?
you mean where x1 came from?
Yeah, I know that x1 is the for the equivalent sign, and x2 is for the first parenthesis, and the x3 is for the second. But how did, like, for example, and came in the second line between x1 and the big parenthesis?
I'm not sure I understand your question. So first of all, I introduced x1. This is a brand new variable, so it doesn't come from anywhere. I introduced it. It's a fresh variable. Actually, x1 represents the entire formula. This is why I put it in front. And
So x1 is the whole first equation.
Yes.
Oh, okay.
And here I also concatenate to this part of the formula the definition of x1. How I define x1? X1 is defined as the implication of the first part of the formula and the second part of the formula. You see?
Okay.
Okay. Okay, but we are not done yet, because I also have to define what x2 stands for. So x2 is defined as this, right? x1 is defined as p XOR not q, and similarly I'm going to define x3. x3 is defined as this part of the formula. So basically we somehow split the formula into separate pieces. Okay, but this is not a CNF yet. So again, what I'm trying to do to translate the formula to CNF. This is not CNF. It almost looks like a CNF because the main operators are conjunctions, but inside the parentheses there are so many prohibited stuff like equivalencies, implications, XORs. This is not allowed. Therefore, we must translate each and every such equivalencies to CNF. This is written here in the last item. Okay, let's see. So let me take the first equivalence here and let me translate it to CNF. So how to do that? Well, I can use, you could do that because you learn this other algorithm which we use in the exercise class. So it would be quite easy to translate this formula to CNF. It's not a problem. Or we could also use this table. So here, the problem is that we don't have a row in the table which is about how to transform an implication. I only have AND, OR, XOR, and stuff. But of course, this is not a problem because you already know we can easily transform an implication to a logical OR, right? Like this. And now I could use this row here. This row. How to translate a logical OR to CNF. So now, basically, I have an equivalence where C is on the left-hand side and plus, that is this junction, is on the right-hand side. Okay, let me use the same notation. So C here, here C stands for x1. So in the table, C stands for x1 in my exercise. Okay, A stands for not x2, and B stands for what? x3. So I hope you get this. I'm just drawing a connection between this row of the table and this particular definition here. Okay, so let me continue then. Meanwhile, if you have a question, please raise it. So now, this is the CNF I should write. It consists of 3 clauses. This is the first clause, the second clause, the third clause. So let's take the first one, A or B or not C. A or B or not C. Okay, so A or B or not C. This is the first clause from the table. So let me now substitute all those literals basically here. So this is the first clause we get. Do you understand that? Guys, are you with me?
Yes, yes, we are translating from x1, x2, x3 to ABC.
Exactly. Exactly. Okay. Okay, then let's continue. Here we have the second clause, not B. This upper line denotes not negation. Actually, this is an alternative notation for negation. Not A or C. Not A or C. So could you tell me what it becomes? Not A or C. Not A or C. What should I write here? Not A, which is now
X2,
x2. Exactly, x2. No,
X2,
oh, come on. X2 without negation, right? Yeah.
yes,
And then C, which is
X3,
X,
X3,
X1.
okay, X1, sorry,
X1,
X1.
right. Okay, thank you. Great. So this is the second clause, and we have a third clause, not B or C, which is, I guess, not B or C. So
X3 or
Not
Negation
X3.
x3
negation X3
or x1.
or X1. Okay, that's it. Okay, thank you. Great. So we applied this table, I mean this particular rewrite rule, and we basically, this is what we did actually. We just translated this part of the formula to this CNF, so you can just copy and paste it and put it here. Great. This is so far a CNF. You see, we have 1, 2, 3, 4 clauses which are connected with the conjunction. So this is how you proceed. Again, you translate each and every equivalence to CNF separately, and then you just plug those CNFs into your formula. All right. Okay, before I finish with this exercise, I would like to stop a little bit and show you an optimized way of this Zetin transformation. So there is a more optimized Zetin transformation because two guys, Plaisted and Greenbaum, figured it out that the Zetin transformation can be further optimized. So this is what their idea is based on. So as you know, each equivalence represents two implications, right? An implication forth and an implication back. And you can raise the question, I mean, those two guys raised the question if we can eliminate at least one of those implications. For example, if you can eliminate this second implication, then immediately you make your situation easier. And this is what they found. This is important. So they found that what you have to do is to check all the occurrences of the variable x on the left hand side. So you just check your formula so far and check if all the occurrences of x are either positive or negative. By positive occurrence we mean they are non-negated. A negative occurrence means it is negated. So if you find out that x occurs only in a positive form, then you keep only the first implication. So this one. This means you can simplify the second implication out. This is really cool. You will see that. In the other way around, if x occurs only in a negative form, then you keep the second implication. So this implication, and you simplify with the first one. Okay, so let's see, why is this cool? So before I plug this CNF here, I check the occurrences of x1 in the formula so far. So this is my formula so far. It, as you can see, it has x1 only with positive polarity, right? Therefore, I can exchange this equivalence to this implication, right? This is what I do. If x occurs only in a positive way, I keep only the first implication, and I completely forget about the second implication, which basically means I can change this equivalence to an implication. Let me ask if you understand this. Or do you think you understand this?
Yes,
A
I
little.
think
Teach it.
It's too complicated.
It's
Yeah,
it
good.
is.
it's complicated. Like 5 minutes after the lecture with the lecture notes, and then it will be like 80-90%.
Mm-hmm.
I think with practice will be good.
Okay, it's not that complicated, you will see. Let me just show you, we have still some time. So how we translate this equivalence. So here you have an equivalence. You learned before that equivalence can be eliminated by translating it to two implications. So this first implication and this other implication, where the direction of the implication is, right to left, something like that. And basically what I did after that, by using the table, I just translated those two implications to CNF. Okay, this second implication is not very nice like this, so it's rather should be written like this. Okay, and now what am I doing? So far my formula looks like this. This is my CNF formula so far. X1 appears only with positive polarity, so without negation. Therefore, I keep only this implication. And I completely forget about the second implication. I eliminate it. I don't need it. This is what Placed and Greenbaum tells me. Okay, if you look at this implication, basically, instead of 3 clauses, you will get 1. You will think about it. Why? It's quite easy to see. So if you eliminate implication here, you get one single disjunction, one single clause, basically. So basically, I got rid of 2 clauses out of 3. And now, this is what I'm going to insert here. Okay, so to summarize this, by using Placed and Greenbaum's idea, you can reduce the number of clauses sometimes very drastically. So and actually it comes for free. It doesn't really require too much to do. You just check the formula so far and you check the polarity of variables. Okay, let me continue. Okay, so here is the next equivalence. So sorry. So this was the first equivalence. I translate it to CNF, and now comes the second equivalence, this one. So I have to translate it to CNF. How to do this? Well, I could immediately go to this table and, well, just check out what operator I use on the right hand side. It is XOR, so I should use this row of the table here. So I would get 4 clauses, 1, 2, 3, 4 clauses out of this equivalence here, if I use the basic Cetin transformation. But you already know that you can use Placid and Greenbaum's idea. So what we have to do is to check X2's occurrences in the formula so far. So can you tell me what polarity does it have in this formula?
Positive?
No,
What?
it's negative. So this is what we call a negative polarity. If we find that the variable x2 is negated everywhere in the formula so far.
Oh,
Okay. So fortunately, it has only one occurrence so far, and it's negated. There are no other occurrences, only negative occurrences. Okay, do you get it?
Yes.
Okay, so x2 appears in the formula so far only in a negative form. Therefore, look at this. We keep only one of the implications. A implies X. So instead of using both implications, we keep only the second one. We eliminate the first one. A implies X. Okay, let's see. So now, basically what we do, we keep only this implication. It's back implication, or it's nicer if I use this form. So we keep only this implication. Do you get this?
Yes.
Okay, cool. Okay, so I'm not going into details. Basically, we can, how to say, we can get rid of 2 clauses of those 4 clauses in this row. So I'm not going to explain this. I'm just writing this down. I hope I will be able to do that. I think the result here will be P Q X2. So this is the first clause we get. The second clause must be almost the same, but with P and Q negated. I think this is it. But if you want to check if my solution is okay, you can just translate this formula to CNF by using the other algorithm you already know. And then you can see if this is the correct solution here. Okay, so I finished with translating this second equivalence to CNF. Let me plug this in here. Okay, here I am. That's all. Okay. Okay, so let's do the same together for the third equivalence. Please help me. What to do with this equivalence? Can we simplify it or we cannot?
can because
I
there is no
I think we can simplify it.
Yes, we can. And why?
there is no negated x3.
That's it. That's it. Very good. So you have to check again what is all the occurrences of x3 in the formula so far, and as Islam just told us, x3 has only one occurrence, only a positive occurrence. Since it has only a positive occurrence, we can keep the first implication. So this one, x implies a, which basically means, in this case, you can simply exchange the equivalence with implication, right? And well, this part is quite easy. I'm pretty sure you could easily translate this to CNF. Let me do it very quickly. Actually, it will consist of two clauses due to the rule of the law of distributivity. Actually, it's not x or q, and what is the other clause? Not x or not r. Exactly. So this is what you have to plug in here. I forgot to put a conjunction. Okay, and that's it. We already translated our formula to CNF. If you look at this, this is really a CNF. It has 1, 2, 3, 4, exactly 6 clauses. It consists of 6 clauses, and that's it. Actually, if you didn't use this optimization of Placid and Greenbaum, the original CTIN algorithm, I think generated 11 or 12 clauses. I'm not sure. You can check this out if you want as a homework. So basically, we have the number of clauses, and that's it. So guys, I think this is the end of the slideshow. Exactly. Do you have any question, any comment at the end?
Will be this lesson uploaded to YouTube?
Well, I hope so. I started to record. Yeah, I recorded the lecture. I hope everything was worked out fine. If the video is okay, I will upload it to YouTube. Yes.
And one more. Can you please share this document?
Okay, no problem.
Thanks.
So will the slides be available on the site?
I cannot hear you.
So I said will the slides be available? The slides.
Yeah. What about the slides?
You'll be on the e-learning site.
Yeah, I will upload them as well. The slides.
Okay. Okay, great.
Okay, that's it. Okay, then thank you for your attention. See you tomorrow.
Thank you.
See you tomorrow.
Bye bye.